everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve the given differential equation which is non-exact. So let's get going. Problem. Solve y plus y square into dx plus xy dy equals to 0. Solution. Given differential equation. Y plus y square into dx plus xy dy equals to 0. Consider as equation 1, which is in Mdx plus Ndy equals to 0 form, which is in Mdx plus Ndy equals to 0 form, where by comparing these two we'll get M and N. Coefficient of differential dx is your M. Coefficient of differential dy is your N, where M equals to y plus y square and N equals to xy. If the partial derivative of M with respect to y is equals to partial derivative of N with respect to x, then we can say that the given differential equation is an exact equation. Now let's find the partial derivative of M with respect to y and N with respect to x. Partial derivative of M with respect to y is equals to dou y of for M y plus y square. Here we are having y in both the terms, right? Since we are doing partial derivative with respect to y, so x will be treated as constant, but we don't have any x here. Is equals to partial derivative of first term with respect to y plus partial derivative of second term with respect to y is equals to partial derivative of y with respect to y is 1 plus partial derivative of y square with respect to y is 2y. Therefore, partial derivative of M with respect to y is 1 plus 2y. Now let's find the partial derivative of N with respect to x. Partial derivative of N with respect to x equals to dou y dou x. So for an xy, since we are doing partial derivative with respect to x, so here y will be treated as constant. Here y is constant. You can write it as y into constant into partial derivative of x with respect to x is equals to y into partial derivative of x with respect to x is 1, which is equals to y. Therefore, partial derivative of N with respect to x is y. So it's clear that therefore partial derivative of M with respect to y is not equals to partial derivative of N with respect to x. From this we can say that the given equation is non-exact. Okay. Since the given equation is non-exact, now let's check whether it is homogeneous or not by adding the powers. So in the first term you're having y, right? Y power 1. You're having 1 here and here you're having 2. Here add the powers 1 plus 1, 2. 1, 2, 2. So you don't have equal powers, right? If you get same powers, then you can say that the equation is homogeneous. Okay? Since the powers are not same, so we'll say the given equation is non-homogeneous. Or you can write the given equation in dy by dx equals to some function of xy form. If you'll get function of kx, ky equals to function of xy, then we can say that this function is homogeneous function. Then the differential equation involving homogeneous function is called a homogeneous equation. Okay, fine. Or directly. And also the given equation is not in y into some function of x, y into dx plus x into some function of x, y into dy equals to 0 form. Right? Now, by observing m and n partial derivatives, we can find the suitable method. Okay? So you're having m equals to y plus y square, right? Take y common from these two terms and you'll get y times 1 plus y. Okay? Now coming to the partial derivatives. Here you're having 1 plus 2y and y. If you want to use 1 by n times partial derivative of m with respect to y minus partial derivative of n with respect to x, we'll get 1 by xy, right? Into partial derivative of m minus y. Here, you can't cancel any single term or you can't get any function of x alone. Okay? We can't use this method. So, coming to m and partial derivatives. You're having 1 here and there is a possibility of cancelling 1 plus y using m and these two partial derivatives by finding 1 by m times partial derivative of n with respect to x minus partial derivative of n with respect to y. 1 by m into partial derivative of n with respect to x is y minus of partial derivative of n with respect to y is 1 plus 2y is equals to 1 by y times 1 plus y into y minus into 1 minus 1 minus into plus minus 2y which is equals to 1 by y times 1 plus y into y minus 2y is minus y minus 1. Take minus 1 common from these two, then you get minus 1 times y plus 1 by y times 1 plus y, right? Or you can write this as minus of 1 plus y. Simply rewrite y plus 1 as 1 plus y by y times 1 plus y. So here 1 plus y gets cancelled as I said you earlier. Okay. So this equals to minus 1 by y. Since it does not involve any x, therefore is equals to minus 1 by y, right? Since it does not involve any x, so we can call it as function of y alone. Name it as g of y, function of y, right? So here our integrating factor will be e power integral function of y into dy. Okay. What happens if you get any real number instead of function of y alone? If we get any real number, say k, then our integrating factor will be e power integral k into dy. Simply we'll write k, that is the real number, instead of function of y. Okay. So this equals to e power integral for g of y. minus 1 by y into dy equals to e power minus integral 1 by y dy, which is equals to e power minus integral 1 by y dy is log mod y. You can write this as e power minus log y, which is equals to e power log y inverse, right? You know that m log n equals to log n power m. If you write minus log y as minus 1 into log y, which is in m log n y form, sorry, n form, you can write this as log y power minus 1, right? The same thing, you'll get the same thing. Is equals to, we know that e power log some function of y equals to function of y. Okay, so since e power log some function of y equals to function of y, then you'll get y inverse. We know that y power minus n equals to 1 by y power n. Then this equals to 1 by y. Okay. See here, g of y means y power minus 1, not the function minus 1 by y. Okay. So here our integrating factor is 1 by y. Therefore, integrating factor is equals to 1 by y. Now, we can reduce the given equation to an exact equation by multiplying it with this integrating factor. 1 by y times the given equation is a exact equation. Consider it as equation 2. You can write this as y plus y square into dx plus xy dy by y equals to 0. If we consider LHS, we are having two terms in the numerator and one term in the denominator, so we can split this into two terms. Then y plus y square by y into dx plus xy by y into dy equals to 0. Then here also you are having two terms in the numerator and one term in the denominator, so we can split this into two terms. Y by y plus y square by y into dx plus here 1y gets cancelled, then you'll get x dy equals to 0. Then y gets cancelled, you'll get 1 plus here 1y gets cancelled. So I'll get 1 plus y into dx plus x dy equals to 0, which is in m1 dx plus n1 dy equals to 0 form, right? Which is in m1 dx plus n1 dy equals to 0 form. Okay, if the partial derivative of m1 with respect to y is equals to partial derivative of n1 with respect to x, then we can say that equation 2, that is the equation obtained by multiplying integrating factor through the given equation, is exact. Okay, so now let's find the partial derivatives of m1 with respect to y and n1 with respect to x. Okay, so by comparing these two, we'll get m1 and n1, sorry. So here we have m1 equals to 1 plus y and n1 equals to x. Now let's find the partial derivatives of m1 and n1. m1 with respect to y, dou by dou y of 1 plus y equals to partial derivative of first term 1 with respect to y plus partial derivative of second term with respect to y is equals to partial derivative of constant with respect to y is 0 plus partial derivative of y with respect to y is 1, which is equals to 1. Now let's find the partial derivative of n1 with respect to x. Partial derivative of n1 with respect to x equals to dou y dou x of for n1 x is equals to partial derivative of x with respect to x is 1. So from these two we can say that therefore partial derivative of m1 with respect to y is equals to partial derivative of n1 with respect to x equals to 1. From this we can say that equation 2, the equation which is obtained by multiplying the given equation with an integrating factor is exact. Okay, since the partial derivative of m1 with respect to y equals to partial derivative of n1 with respect to x, from this we can say that equation 2 is exact. Okay. Now we need to find the general solution to the given equation, right? So the general solution of equation 2 is the general solution of the equation 1. So we can find the general solution to this using inspection method or exact equation method. Okay. Firstly, we'll see inspection method. So this is the reduced form of 2. Equation 2 is 1 plus y into dx plus x into dy equals to 0, right? You can write this as 1 into dx is dx plus y dx plus x dy equals to 0. Since we know that differential xy equals to x into differential dy plus y into differential dx, then you can replace y dx plus x dy by differential xy, then you'll get dx plus differential xy equals to c. Now integrate on both sides. Simply perform integration. Then you'll get integral dx plus integral differential xy equals to 0. Then integral dx is x plus integral differential xy is xy equals to integral constant c. Then if you take x common from these two terms, you'll get x times 1 plus y equals to c. Okay. Since we know the formula of differential xy, which is x dy plus y dx or y dx plus x dy, so it is easy to use inspection method. Okay, but in some cases you can't identify differential formula. Okay, there arises a complexity. So instead of using inspection method, we'll go for exact equation method. Okay, we know the general solution of exact equation, right? Therefore, we know that the general solution of an exact equation m1 dx plus n1 dy equals to 0, that is an exact equation of the form m1 dx plus n1 dy equals to 0 is given by integral over x m1 dx plus integral of terms of n1 free from x into dy equals to c, right? Consider the first integral integral over x m1 dx. Here we'll be integrating m1 with respect to x, treating y as constant. Is equals to integral for m1 1 plus y into dx is equals to integral 1 dx plus integral y dx is equals to integral 1 dx plus integral dx plus, let's write the constant y outside the integral, will get y, that is constant integral dx equals to integral dx is x plus y into integral dx is x, which is equals to x plus xy. To take x common from these two terms, you'll get x times 1 plus y. Okay. Therefore, integral over x m1 dx is x times 1 plus y. Now consider the second integral, integral of terms of m1 free from x into dy. So here you are having n1 equals to x. So terms of n1 free from x is 0. Integral 0 dy is 0. Therefore, the general solution of 1 is the result obtained from the first integral x times 1 plus y plus result obtained from the second integral 0 equals to c, or x times 1 plus y equals to c is the required general solution. Okay. So this completes the problem. So we have seen a problem from non-exact equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.